Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson. Today we're going to be discussing a problem involving the evaluation of an integral using the limit of a sum, which is, in some respects, the definition of an integral. If you have any questions about this problem, please feel free to put them in the comments below. And if you have any other problems that you'd like to see done, please feel free to put them down there as well. So let's jump into this. So the problem asks us to use the limit of a sum to evaluate the integral from -1 to 2 of x cubed minus x squared to minus 2x dx. Also remarks that if you're off after checking, to not erase your work. Because there's a lot of calculations to this, and there's a lot of pieces that, if you don't do things quite right, can kind of go wrong, especially if you're getting an actual number out of it. So below, I've already written down the definition of the integral in terms of the limit of a sum. And it's the limit as n goes off to infinity of the summation from I equals 1 to n of the function evaluated at some x value times a change, the width of the interval for that particular x value. Now, for our problem, our delta x sub I is going to be a fixed amount. And so we can say that delta x is actually equal to b minus a over n. Sometimes it's not. Sometimes you can take the widths of rectangles, of different rectangles for each interval, and that gets into different problems. But for us, it's just going to be the same thing for each interval. So let's go and fill in our numbers for each one here and start to take a look at what we're going to need to find this limit. So we're going to go from -1 to 2 of x cubed minus x squared minus 2x dx. And so that's going to be equal to the limit, now as n goes off to infinity, of the summation from I equals 1 to n of x sub I cubed minus x sub I squared minus 2x sub I times, and then I'll go ahead and put in the values that we have here, 2 minus -1 all over n. For, if you knew what the number of subintervals, you would put that in for n, but n's going off to infinity, so we're not going to be plugging anything in for n there. So what do we need to find? Well, looking at our limit of our sum, we need to figure out what the x sub i's are. And sometimes you get a formula for that. If not, you have to make it up. But in general, the formulas for your x sub i's looks like this. It's x sub I is equal to your initial starting point, your left end point for your integral, plus I times delta x. So that should get you between all the x sub i's. A lot of assumptions there. The main one being that the x sub I, each x sub I is the same distance toward each other, or from each other. And sometimes that's not the case. But in this case, we're gonna say that they're all the same distance from each other. So for our problem now, this gives us something to figure out. So each x sub I for us is going to be equal to -1 plus I times, and then our delta x. And our delta x was 2 plus 1 over n, or 3 over n. So now we're going to plug this in for each of our x sub i's, and we're going to get a fairly decent mess, but it's going to be a workable mess. Just got to take it one piece at a time. This problem is not a short one, generally. But if you know each step, it generally turns out to be a doable one. Okay, so now I've put in -1 plus 3 over ni into each place where x sub I was, and then multiply that whole thing by 3 over n. And now what we need to do is get everything FOILed out. And so that means you're going to have to cube out -1 plus 3 over n I and square out -1 plus 2 over ni squared, and then distribute the 2. It's, like I said, it's very tedious, but just take it one piece at a time and just gotta grit your teeth and get it done. Okay, so now I've gotten everything expanded, and hopefully I didn't make any mistakes. Okay, so I've corrected all of my mistakes and got everything cleaned up. So now I need to combine like terms and then get out the number over n in there. So I'm just left with a bunch of I squared, I cubed terms. So it looks like the -1 and the 2's cancel. So as I finish up combining everything and then putting everything in order here, you see that I'm left with 3 different terms. One involving I, then I squared, then I cubed, and then all of this is going to be multiplied by 3 over n. So I'm going to distribute that 3 over n into each one of those terms, and then I'm going to separate each term into its own sum. So that's what you'll see on the cut to the next picture here. So I've distributed everything in, and I've separated the sums into, those 3 terms into their own separate sums. Now the next step that I'm going to do is I'm going to pull out each of the number over n's. I can do that because the summation is only acting on I, and it's the limit that's acting on n. So I can pull those out, and I'll just get the sums of I, the sum of I squared, and the sum of I cubed. Okay, so there's my sums with the number over n's pulled out. Now somewhere in your handout or your book, you should have a table that lists out the sum of the different powers of I. So, for example, the sum from I equals 1 to n of I is equal to n times n plus 1 all over 2. And you should have one of those for each summation. So those formulas there should be in a table in your book somewhere. They may look a little different, but the values will be the same. So for each sum, I'm going to replace it with the n form of that sum. Okay, so now I've replaced each of those sums with their formulas. And now what I have to do is, I don't have to, but it's going to be easiest to go ahead and expand each of those factors on the top of each of those formulas. So I've expanded each of those terms, each of those factors up on the top. And now I've got my 9 over n squared times n squared plus n over 2, etc. So the next thing I'm going to do is, there's some ways to shortcut, which we're going to do next, but I'm essentially going to go ahead and distribute each of those numbers to the polynomial next to them, and then get them all into one fraction, each group into its own fraction. So now I've got all of that distributed. Now we can take the limit of this, essentially. There's one more step that you could do, and I'll go ahead and put it up so that you can see what that looks like. But the idea here is that when we take the limit, the only thing that's going to matter are the coefficients of the terms where the variables and the exponents match. So for the first one, we're only worried about the 9 over 2. The 9n over 2n squared, well, the n squared is going to go to 0. Or is going to go to infinity faster than the n, so that whole thing's going to go to 0, and so on. But I'll go ahead and turn each of these fractions into more fractions so we can see exactly what we're looking at. Now, if I simplify them, you'll find that there are a few where the variable on top cancels completely with the variable on the bottom. Those are going to be our useful ones. But the ones where the variable on top has a lower exponent than the one in the bottom, when I take n out to infinity, we get a number over infinity. And that, we're told, is defined to be 0. So any one where the exponent on the top is smaller than the exponent on the bottom, each one of those fractions is going to go to 0. Cross them out, show that they're 0. And now we can take the limit, which is just those numbers that are left. So I've got 9/2 minus 216 over 6 plus 81 over 4. And if we go ahead and evaluate that, that ends up being 45 over 4, negative 45 over 4. So that's what our answer should be. And if we find the integral by using normal means or using a calculator, we can see if we got the right answer. And of course, we're off. The answer was negative 9/4, and we're off by 9. So let's see here. Okay, so I had made a mistake. It's a rather small one, and we can push it back through the problem fairly quickly. So this 3 over n right here should have been a 9 over n. So I'm going to make that fix there, and then we'll go that on. That's 9 over n, 9 over n. And so that means when you distribute that 3 in there, this will become 27. I'll make that 27 right there. So nothing else needs to change, just that 9 needs to become a 27. Okay, so now when we add up all of these, we do indeed get 9/4. So that gives us the right answer. So it just goes to show that it's very easy to make a mistake in these problems like this. So that should do it. That finishes out that problem. Now, thanks for watching, and I'll see you on the next problem.